This video is an overview of Taylor polynomials. So what are these things? Well, sometimes it's useful, as I've said here, to have a polynomial that mimics a particular function rather than using the function itself. For example, we can approximate sine of x quite well by just using the straight line y equals x if x is close to 0 and we're measuring in radians. So you might be asking, what does close to 0 look like? Well, a picture can help. Over here I have my function y equals sine of x, and over here I have my line y equals x, and you'll notice that if I pick values, x values between about minus 0.4 and 4, then the two graphs lie on top of each other, so we might as well say that sine of x is almost equal to x. So if one day you need to approximate the sine of, for example, 0.2, you don't have to get your calculator out, you can just say, well, it's close enough to 0.2. But notice here that what we're really saying is close to means x lying between about minus 0.4 and 0.4. Suppose you want a better approximation of sine of x. Well, you can use a cubic. So we can approximate sine of x for x near 0 with x minus x cubed over 3 factorial, where again we're only saying our x values need to be near 0 and our x is in radians. Let's have a look at a picture of what this means. So over here in blue I've got my line y equals sine of x, and in black I've got the line y equals x, which was our first approximation, and then in red I've plotted our new approximation, which is y equal to x minus x cubed over 3 factorial. And if you remember, the range that we could use successfully with our line y equals x was really only about minus 0.4 to 0.4. But if you imagine now that we're using our line x minus x cubed over 3 factorial, suddenly we get a very good approximation for values of x lying about minus 1 to 1. So you can see that for those values, our red line, which is our approximation, lies almost completely on top of our sine of x, which is what we're trying to approximate. So this gives us a good idea of using polynomials and what happens. If you add higher order terms, so you use a higher order polynomial, then you're going to get a better approximation, and it's probably going to be valid for a wider range of x values. So where did the two polynomials that we used to approximate sine of x in the previous example come from? Well, it turns out that they're both examples of Taylor polynomials, which are probably the best way of estimating a function near a particular x value if you want to use a polynomial. To find the Taylor polynomial approximating a function, you need three things. So the first thing that you need is the function that you actually want to approximate, obviously. And notationally, we're going to refer to this guy as f of x. So in the examples that we just looked at, we had that our function to approximate was sine of x. The next thing that you need is the x value around which you want to do the approximation. And we're going to call this particular value a. So although we didn't say anything explicitly in our previous examples, we were using a equals 0. So we were looking at approximations of sine of x for values near x equals 0. And the third thing that you need is the order of the polynomial you're going to use for your approximation. which is generally referred to as n. So in our first example, we had sine of x equals x. Notice that x has order 1. It's a first order polynomial. And in our second example, where we had sine of x equal to x minus x cubed over 3 factorial, this was an order 3 polynomial because the highest power of x is 3. Once you've got all the details of what it is that you're going to do, you can find the Taylor polynomial of degree or order n around x equals a using the following. So notice that on the right-hand side we have the equation for a polynomial. And if you look at each term, for example, if we look at the term that has an x squared in it, then we're going to use the second derivative of our function evaluated at a as the coefficient of that term, together with dividing through by 2 factorial. And we're going to find up to the nth derivative for the final term, which is going to give us an x to the n term, and we're going to divide that by n factorial. So let's look at an example. So now I'm going to work out, let's find the third order Taylor polynomial for sine of x around 0. So what does this tell me? This tells me that my n is going to be 3, that my f of x is going to be sine of x, and that my a is going to be 0. Because I'm working with n equals 3, I know that I'm going to need 3 derivatives. So I'm going to say, here's my function, sine of x. Let's find the first derivative. That's going to give me a cosine of x. Second derivative is going to give me a minus sine of x. And my third derivative is going to give me a minus cosine of x. You can pick your own notation. You can carry on using primes. So I could have also written my second derivative as f double prime, or you can use the notation that I did here, where I put 2 in brackets to tell me that's my second derivative, or you could equivalently use the notation using little Roman letters, whatever makes you happy. So you'll notice if you go back to the formula for the Taylor series, I don't substitute f of x into my Taylor series. What I actually need to substitute in is f evaluated at a, which in this case is 0. So I go ahead and work out f at 0. Sine of 0 is just 0. I also need my first derivative evaluated at 0, and cosine at 0 is equal to 1. Second derivative evaluated at 0 is going to give me a 0, and my third derivative evaluated at 0 is equal to minus 1. If I just write out the formula for a third order Taylor series, I've got f of x is equal to f evaluated at 0 plus first derivative evaluated at 0 times x, because this would have been x minus a, but my a is 0. Then my next term is my second derivative evaluated at 0 times x squared, all divided by 2 factorial, and my third term is the third derivative evaluated at 0 times x cubed all over 3 factorial. And if I plug in the values that I've just calculated, then what I'm going to find is my sine of x is approximately equal to f at 0, which is 0, plus my first derivative times x, which is just x, plus my second derivative, which is 0 times x squared, and then my third term is going to be minus x cubed over 3 factorial, which is x minus x cubed over 3 factorial. So now you can see where that polynomial came from in our earlier examples. So we've seen that as we add more and more terms onto our Taylor polynomial, it becomes a better and better approximation for our function. And the question you might ask is, well, what if we take infinitely many terms? So what happens if we let n go to infinity? Well, if we do that, what we end up with is a series rather than a polynomial, and what we've got is a Taylor series. But a few other things happen as well. So it turns out that if you actually have infinitely many terms, then your approximation becomes exactly equal to. So that's what happens when we go from a Taylor polynomial to a Taylor series. So if we were to write out the formulae for each of these, for the Taylor polynomial, we have f of x is approximately equal to the sum from k equals 0 to n, which is the order of our polynomial, of the kth derivative evaluated at a times x minus a to the k over k factorial. So that will give us something with n plus 1 terms. And it's an approximation. But if we head over to the Taylor series, then what we have is that f of x is exactly equal to the sum from k equals 0 to infinity of the same thing. So f of k, kth derivative evaluated at a, x minus a to the k over k factorial. But what's different here is our series has infinitely many terms, and it's exact. So let's get a little bit more detail on Taylor series. So the first thing is there are several Taylor series that once you've worked them out a couple of times, you should just memorize, because they're going to come up again and again and again. And here they are. There are 2 further videos on YouTube that you can have a look at to see some of the other things that we use Taylor series for.